Hi everyone, my name is Zimeng Lyu. I'm a PhD student in Rochester Institute of Technology. The second paper I'm going to present today is Improving Distributed Neuroevolution Using Island Extinction and Repopulation. The motivation of this work come from our in practice, because in distributed evolutionary algorithms, sometimes we have islands are distinct from each other. So sometimes we'll have islands that get stuck at local optima and stop evolve better. So throughout the entire process, we can see from the two examples here, they are not doing better, or there's no chance that they will get evolved better and better. So actually, it is a waste of the computation resources if we know at the beginning that those islands were gonna stuck here forever and not getting better. So we have a research question that can we extinct and repopulate those islands to improve the evolutionary algorithms performance? And also, as far as we know, there is no other research that doing repopulation on neuroevolution. So the framework we use is EXAMM, and EXAMM is a distributed neuroevolution algorithm for involve large recurrent neural networks. The recurrent neural networks is used to predict the real-world time series data set, and it would allow deep recurrent connections that will connect the current time step to the previous time step. The EXAMM involve different memory cells, and it is also a scalable distributed parallel program, and we have MPI and multi-threaded version of this framework. And we evaluate the fitness of the genomes by mean squared error on the validation data set. Original EXAMM have two states. One is initialization state, the other is field states. So one is in initialization state. Each island would have a copy of seed genome. The seed genome is a fully connected minimum genome that only have connections between input to output. There's no hidden layer. And islands are filled with mutated genome that's randomly selected from this island. Then we reach to the field state. The field state will have a group of islands that each has a maximum capacity, and the genomes on each of the islands are ranked by their fitness. So the first genome on each of the island is the best genome on that island. And one genome is generated for each island in a round-robin fashion. So one genome will be generated for island 1 genome will be generated for island 2, and so on. And it rotates in this way. For the current island I, we have different ways to generate a genome. We have inter-island crossover that one parent is randomly selected for the current island, and the second parent is the best genome from a randomly selected island. We can also do mutation that the parent of mutation is randomly selected from the current island. Or we can do intra-island crossover that two parents are randomly selected for the current island. And the genome generated is generated for the current island. And then the generated genome would be sent to the worker process. The EXAMM use asynchronous worker scheduler, which means the workers don't wait for each other to start a new run. Whenever a worker is available, it will send the genome it will take a genome and start to train and evaluate it. And when the genome is finished training, it will get evaluated and inserted back to the population. Because all the genomes in an island is ranked by their fitness. So this genome is only inserted back when it's at least better than the worst genome on this island. And now we will talk about our proposed strategy, that is extinction and repopulation strategy on EXAMM. The repopulation step look like this. So when all the islands reach the field states, the islands will be periodically ranked by its best genome's fitness. which means they are ranked by their first genome's finish. And then the worst island will be erased and repopulated with the mutated global best genome. So each time once these islands turn to have a new generated genome, EXAMM will take the global best genome, mutate it m times randomly, and insert it and send it to worker to train, and it will return back to this island. We have extinction and repopulation strategy that will allow repeatedly or not repeatedly repopulation. When we have a no repeat repopulation, that the repopulated island probably need some time to evolve and get better when they have new genes. So we'll give them a extinction events time before it can be erased again. For no repeat extinction, that we will just repopulate this island by its performance, regardless of when it's getting repopulated. We have the second rule, because in practice, we have learned that in most of the times, if the island is not doing well when we evaluate it, there is a really slight chance that it will get better again. So it will stuck at the local optima. So we have a brief overview of what we said, and we will go over how EXAMM repopulation states work. With the initialization state, everything stayed the same, that the new genome is generated by randomly select a parent from the current island, do a mutation, and train and send it back. For field states, it's also the same, that we can do crossover or mutation on the parents and generate a new genome. For repopulated states, for the current repopulating island, we select the global best genome and do mutated m times and send it to worker to evaluate and eventually insert it back to this repopulating island. And now we can talk about the experiments. We used two data sets. One is the coal-fired power plant data set. The other one is aviation flight data set. And we can see those are the example of how the output parameters look like. First, they look very different. And second, they are not seasonal data. We used RIT's research computing cluster to do our experiments. We used the 72 cores for all the experiments. For the hyperparameters, we have number of islands is 10, island capacity is 10, mutation rate at 70%, intra-island crossover rate at 20%, inter-island crossover rate at 10%. For each experiment, the total number of genome generated is 20K, and each generated genome will get trained 10 times in the worker. We evolve simple neurons as well as memory cells. All the recurrent edges that EXAMM generated could span any time gap randomly between 1 and 10. So for the experiments, we compared the island extinction and repopulation strategy with EXAMM baseline. That means EXAMM baseline is the original EXAMM that does not have repopulation strategy. We also compare with need speciation strategy on both of the data sets. Those are the parameters that we test. We test if it's being repopulated repeatedly. It can be repopulated repeatedly or not repeatedly for 2 extinction events. So if the islands are not getting repopulated repeatedly, it will wait for 2 extinction events then to be considered to be repopulated again. We have different extinction repopulation frequencies at 1,000 and 2,000 genomes getting generated. We test different number of mutations to apply on the global best genome and see how that performs over different number of mutations. All the experiments are performed for 20 repeated times. Now we can move to the results. Let's take a look at the original graph that we showed at the beginning of the talk, that some islands get stuck at the local optima, does not get better. And this is the EXAMM repopulation strategy that if you see a vertical line for those islands, that means this island is being repopulated because when you erase this island and then send a new generated genome to worker, the fitness of this island is reached infinity. And when the new generated genome get returned by the worker and sent back to the population, we can see this island actually get out of its local optima and start really good during the whole process. And this is true for other islands as well. And we can see towards the end of repopulation, we can see there are a couple islands that's at the end here. Those 3 islands are actually, all of them are repopulated islands, which means this repopulation strategy actually works and can improve the overall performance of this evolutionary strategy. This is the convergence rate on the whole data set. Over different hyperparameters, we have different extinction frequency, we have repeat and non-repeat extinction with a different number of mutations applied on the global batch genome. The value range here showed the value range over 20 repeated runs, the minimum value and maximum value on the performance, and the line in the middle is the average performance. First, we can see all the EXAMM experiments are doing better than the NEAT strategy, and the EXAMM baseline is the blue line in here. And actually all the test cases are outperform the EXAMM baseline by average. And also having number of 2 mutations doing slightly better than the other strategies for 3 of the cases here by average. Very similar results for the aviation data set, except for the no repeated runs, we don't see a big difference between different test cases. And those are the statistics over the 2 data sets on all the experiments of over 20 repeats. First, by average case and the best cases, we can see actually the no repeated runs, the extinction has slightly better results and actually has all the best performing cases in here, even though those 2 numbers are same. But overall, no repeat is doing slightly better, but it's not very obvious. And in general, having extinction frequency at 1,000 is doing slightly better than 2,000. And also for the number of mutations, having mutations is definitely doing better than not having mutations. But actually having number of 8 mutations is doing really bad. That's because when you have excessive number of mutations, you add too much variety to the repopulated island. So you will have, in most of the cases, would perform worse than applying 2 or 4 number of mutations. And the p-values here are the statistical significance test. When the number is marked in bold, it means there's a statistical difference between the different experiments against the EXAMM baseline. And we want to take a closer look at each island and to learn how many times can one island be repopulated. So this graph show how many times an island can be repopulated by average over 20 repeated runs. For example, the graph here, when we have 0 mutations, there are 4 islands that will be repopulated once throughout the entire process. And there is a big difference between extinction frequency at 1,000 and 2,000 here. That's because with a fixed number of total genomes get generated, there are more extinction events for extinction frequency at 1,000. And between repeated run and no repeated runs, we can notice slightly that allowing repeated repopulation on some islands. Those islands are frequently get repopulated, especially for repopulation of 5, 6, 7, 8, 9, 10 times. The chance of this island getting repopulated, there's more islands get repopulated for more times for repeated runs. Also similar results for the flight data set, that when we have repeated runs, the islands is getting the islands getting more frequently to get repopulated for more times than no repeated runs. We reached our conclusion. This work proposed the island extinction and repopulation strategy in neuroevolution, and this repopulation strategy outperforms EXAMM baseline and NEAT. The mean EU test shows statistical significance between EXAMM baseline and most of the test cases. With extinction frequency at 1,000, it generally performs better performance because we have more times to evolve, to erase and repopulate, so it's evolved faster. The no repeated repopulation had slightly better results because newly repopulated islands has more time to evolve before being evaluated and repopulated again. And applying more than one mutations could speed up the evolutionary process, but having too many mutations at once might bring excessive variety to the new island population. And that's all for my talk today. Do we have any questions?
Thanks a lot. And so are there any questions from the audience?
Hi, hello. I have one quick question. Thank you for the talk. I really enjoyed it. I was wondering, when you compared with the EXAMM baseline and NEAT, how did you guarantee that the comparison is fair? I mean, the models have different behaviors. So did you adjust the parameters to make sure that the comparison between different approaches was fair? Sorry.
Yeah, that's actually a really good question. To have a fair comparison, we actually implement NEAT in our framework because of our asynchronous strategy, and we're using C++ because C++ generally performs at least run faster than Python code. And also NEAT originally does not evolve recurrent neural networks. So we have to re-implement it to generate recurrent neural networks. The only difference is the speciation strategy. All other things are same. And also NEAT does not train genomes, it just uses random weights. So to be fair, we would allow it to evolve for longer than EXAMM.
Yeah. That was something that I was thinking, that you might have to allow NEAT to run for a little bit longer to at least try to be fair. Thank you for the answer.
Thank you for the question.
All right. Any other questions? If not, I have one. If I understood correctly, I'm not sure I got this part, but basically you decide which island to extinct and repopulate once every 1,000, 2,000 genomes have been created, something like that.
Yeah.
Have you considered trying, instead of doing it at precise intervals of time, trying to detect some sort of stagnation in the island? So if I don't know, something like the best fitness of the best individual in the island doesn't change over a few iterations, then extinct the island.
It's really hard to say because most of the islands would reach almost the same speed of convergence, except that some of them have higher performance, some of them have lower. But overall, because evolutionary algorithm only care about the global best genome, so we don't care the last 5 islands at all. So we will just take the last one, repopulate it, and later take another last one and repopulate it. the overall global best genome is not getting touched. The best island is not getting touched.
Okay,